Okay, so what do we mean by Venn diagrams? First, why do we call these Venn diagrams? Well, John Venn was a British mathematician who is responsible for these circles. I am not exactly sure what else Venn did. I am not sure if I would like to be remembered by just for these circles. You know, if I were Venn, I'm not sure if I'll be happy that the rest of the world will call this Venn diagram, and that's the only one thing that you are known for long after your death. But that's what happened, okay? So the Venn diagram sometimes looks like this, sometimes looks like this, and sometimes looks like this. And sometimes you have three circles, you know, maybe intersecting with each other. So these are Venn diagrams, okay? What do we use this for, okay? Well, if two sets can be related to each other, they are related in three different ways. Okay, so you're thinking of, you know, like, let's say we're talking about like all birds can fly, or living in America, California implies living in the US. We are talking about two sets of people or two sets of objects like flying objects and birds, right? Okay, so two objects or two sets can be disjoint. Set A can be completely separated from set B. Here's an example. Maybe A is a set of all dogs, and B maybe the set of all cats. Okay, now do you agree that these are disjoint? Do you agree with that? Do you agree that these are disjoint? Yes, of course, because all dogs are non-cats and all cats are non-dogs, right? So there's no animal in common. In other words, saying that no dogs are cats. Okay, that's a statement, okay? In other words, this is saying if you are a dog, you cannot be a cat. Or if you're saying if you are a cat, you are not a dog. Or you're saying if an animal is a cat, it cannot be a dog, or if an animal is a dog, it cannot be a cat. Now, many times, you will also see two sets where one is a part of a bigger set. Okay, this is called a subset relation. A can be the set of all dogs, and B can be the set of all cats, but B can be the set of all animals. Okay, now this would be an English statement. All dogs are animals. Sorry, yeah, that's right. All dogs are animals. That would be a universally a quantified statement, right? Remember your universal quantifier? This is saying every dog is an animal, or all dogs are animals. It's also saying, in terms of a conditional, if X is a dog, X is an animal, okay? Or if you're a dog, you are an animal, okay? Or if Spot is a dog, then Spot is an animal, okay? So that would be an if-then statement. Showing you this subset relation. And this is probably the most important relation among the other ones, okay? Because we'll be talking about if-then statements, and listen carefully, every if-then statement, maybe I should write this down. Every if-then statement can be constructed or drawn or visualized in terms of the subset relation. Okay, where the if part is the inside circle and the then part is the outside circle. And then there are, again, the most common one is just an overlapping, but not subset and not disjoint. Okay, an overlapping relation would be something like this. Some A are B. Some dogs are, what do you want to say? White. No, let's just say, I'll stick to my notes. Pets. Okay, because there are, you know, okay, so these are dogs that are pets. But then there are dogs that are not pets, right? Maybe they live in shelters, they're not pets yet. Maybe they're stray dogs. And then there are pets that are not dogs. Maybe those are cats. Maybe those are, what else do people have? Birds, you know, or snakes. Some people, I guess, have fish as pets, and certainly they are not dogs, right? Okay, so these are the three different ways that two sets can interact with each other. All right, let's draw a diagram. All of these universal, existential quantifiers can be drawn with the Venn diagram. When we say all whales are mammals, by the way, that happens to be a true statement. Here are the whale circles. Here are the mammal circles. Now, this is, by the way, I haven't used any numbers here, but this is a very mathematically important topic of sets. In fact, you can think of mathematics as a study of sets. So, and you say, well, I don't know, this doesn't sound like a math class. Okay, I want you to know these are probably more mathematical than anything else you have ever studied in your math class or an algebra class. Okay, these are called foundations of mathematics. They're called, sometimes called a part of meta mathematics. Okay, all right, all whales are mammals. All whales, if you're a whale, you have to be a mammal. That's what this Venn diagram is showing. Okay, next, no fish are mammals. Do you see which one of these relations this is? Clearly, this is disjoint. Here's the fish circle, and here are mammals circle. Okay, so this means no fish is a mammal, no mammal is a fish. And of course, that is also a true statement. You say, how about whales and dolphins? Well, you know, these are mammals, not fish. Right? Okay, some doctors are women. So that's which one? Some doctors are women. So that means there exists at least one woman that's a doctor, right? So that's a overlapping relation. So we have female doctors here. We have male doctors here. We have women who are not doctors. And there's me, right? Because I am not a doctor and I am not a woman. So, okay, so that's how you can draw Venn diagrams for these. And the reason we are studying Venn diagrams, and you will be drawing these for your homework, is because these are extremely useful in checking for validity, okay, in formal logic. Here is and again, this is the important part of this lesson, okay? So make sure you understand how you check for validity of an if-then argument or a deductive argument using Venn diagrams. Look at this. It says all fish live in water. All fish live in water. So that means okay, every fish is something that lives in the water, right? So you have fish in the inner circle. So this is also saying if you are a fish, then you live in the water. Okay, maybe I can write this down. If fish, okay, I'm abbreviating. If you are a fish, or if X is a fish, then you live in water. If X is a fish, then X lives in water. So here's the fish, and a bigger circle is whatever live in water. Okay, you can say things that live in water. Okay, this one, I mean, the statement is saying this: if X is a fish, then X lives in the water. All fish live in water. Okay, now look at the second statement. It says whales are not fish. All right, so where are the whales? All this is saying is it's not inside of the inner circle. The inner circle consists of fish. So the second statement only tells you whales could be here. Whales could be here too, right? Just by reading these two statements, okay, you don't know where the whales are. The only thing you know is that the whales do not belong to this circle of fish because it says whales are not fish. Okay, so therefore whales do not live in the water. Is that a valid argument? No, because we can't conclude that whales are here outside of the live in the water circle, not because you know what a whale is. Okay, so by the way, this applies even if you don't know what this thing called whales are. Okay, because the only thing the second statement says is that whales are not fish. So the whales are not inside of this inner circle. Whales could still be here, still be here. Okay, so you cannot determine or conclude that these objects called whales are inside of this outer circle or outside of the outer circle. And so this conclusion is not valid. Okay, do you see that? Because based on these two circles, you cannot determine if the whales are outside of this outer circle or inside of the outer circle. All you know is that it's outside of the inner circle. So it's not valid. And by the way, you know it's not true either, right? Because you just happen to know what whales are, and you happen to know that these whales live in the water. Okay, so this is the first statement is true. All fish live in water. Okay, I mean you can't imagine a fish living outside of the water, right? Okay, I mean there are other things that live in the water, but all fish do live in the water. And whales are not fish. That's also true. Okay, so this is true. This is true. but it's not valid. So it's not a sound argument. Okay, so let's check for the second statement. All US presidents have been men. Now, many of you may say, oh, unfortunately, that's true. Okay, maybe it's going to change. All right, it may change, but at this point in history, as of the recording today, in 2020, all US presidents have been men. All right, so how do you draw that? Presidents should be the inner circle. Okay, remember the first thing that appears. This is actually saying if X has been a US president, then X has been man. That's an if-then statement corresponding to this universal statement. If X is a US president, or if X has been, or if X was a US president, then that person belongs to the larger group of people called men. So this is the Venn diagram representing the relationship between the set of all things called US presidents and set of all things called men. Abraham Lincoln was a man, right? Right, and therefore Lincoln was a president. Now, of course, we know Lincoln was a president, but is this a valid statement? Okay, you may want to pause this for a little bit and think in terms of this Venn diagram and come up with an answer. Very important question here. The answer? This is not a valid argument, even though the conclusion happens to be correct. Why is it? Okay, so based on this first statement, I have drawn the circle, two circles, right? Well, president circle and the man circle. Abraham Lincoln was a man, so all we can conclude is that Lincoln may be here or maybe here, right? We don't really know based on the second statement where Lincoln is. All it says is Lincoln is a man. So that does not give you this conclusion as a valid conclusion. It's not valid, okay? Even though this statement happens to be true and this statement happens to be true, right? Why is it not valid? Because the conclusion is also true, right? The reason it's not valid is because based on these two statements, you do not know that this Lincoln L belongs to the inner circle or the outer circle. All we know is that it does belong to, or it's inside of the outer circle, but we don't know if it is inside of the inner circle. All right, so this is a case where not valid, but the conclusion and each statement is true, okay? I know it's confusing, but every statement can be true without the argument being valid, okay? And unfortunately, we see this in many cases. If you watch the news and if you follow the politics, okay, this is all over the place, right? So people can be saying true things, but their argument could be faulty. And you don't want to do that, okay? Because people can point out, hey, this person doesn't understand the argument. This person doesn't understand logic. So how can we trust this person if he or she does not realize this is not a valid argument, okay? All right, so let's check for another validity in another situation. If it's Tuesday, the bank is open. And by the way, when you analyze these things, you may want to forget if each statement is true or not. Okay, regardless of what each statement means or if each statement is true or not, validity is independent of the meanings. And in fact, even if you don't know what these words mean, you know, if I say, say, hey, if it's Blur's Day, the is open, okay? If it's Blur's Day, is open. And you have no idea what I'm talking about, but you can still check for the validity of an argument. That's an amazing thing about this, because the validity is a logical structure and it is independent of the semantics, okay? All right, so let's try to analyze this by drawing pictures. If it's Tuesday and you have lots of Tuesdays in the calendar, then the bank is open. So Tuesday happens to be in the inner circle of the days when the bank is open, right? Tuesdays and open days. Today, the bank is closed, okay? So today the bank is closed. So where is today? Well, you know today has to be here because the bank is closed. It's not, today does not belong to days when banks open, right? And therefore, it's not Tuesday. What is it saying? This is saying today, the day called today belongs to the outside of the outer circle. There is no way, therefore, that today belongs to or is inside of the inner circle, okay? Because Tuesday is one of the days when the banks are open. If banks are not open today, or if the bank is not open today, it cannot be inside of the Tuesday circle, because if it were Tuesday, then the bank would be open. This happens to be a valid statement. Did you get that? This is maybe the first statement you see it's valid, right? If an object is outside of the outer circle, then it cannot be in the inner circle, right? Very, very important, okay? Again, you may think, oh, this isn't really not like math, let me go back to algebra. Well, no, don't do that, okay? Because this is probably more important in your life, more important mathematical skill in life than, traditional algebra class. I'm not saying algebra is not important. It is important, and I endorse it. I teach calculus, I teach algebra, but this stuff is really important as a citizen of this society, okay? If you live in life, you will have to start thinking logically, and this is very important. Even as a taxpayer or as a citizen, as somebody who votes. Okay, all right. So if it's Tuesday, the bank is open. Today the bank is not open, and so you are an outside circle. Now you may think, you know what, that's not true, because because let's say this Tuesday is Christmas, and Christmas could happen on Tuesday, and the bank will certainly be closed. So this is not true, right? You're right. This is not a true conclusion, but I am saying this is still valid. You know where the argument is faulty? In other words, today could be a Tuesday, which is also a holiday, and the bank is going to be closed, right? So you can't always conclude that. Okay, you're absolutely right. What went wrong is this hypothesis, or this, what we call the major premise. If it's Tuesday, the bank is open. That's not true, right? Okay, again, you can make a sort of a realistic or practical counterexample. If that Tuesday falls on a holiday, like the Memorial, Memorial Days are never Tuesday, but a Christmas could be a Tuesday. New Year's Day could be a Tuesday. Many other, 4th of July could be a Tuesday, right? And the bank would be closed. So this first statement is actually not true. But if the first statement were true, and if the second statement is true, then the valid argument will give you a true sentence. And in that case, this will be called a sound. So here's a good example of a valid argument, but not sound. Sound means that each statement is true, and therefore, and the argument is valid, and therefore it is true. So let me go ahead and say this again. Sound means that every sentence is true, and the argument as a structure is valid. Okay, in this case, it is valid, but the first statement does not have to be true, because again, Christmas could be a Tuesday, or 4th of July could be Tuesday, and the bank would be closed. So this is not a sound argument, even though it's a valid argument. You see the difference? You may have to listen to this again. And that's a nice thing about video lectures, right? You can go back and watch this over and over until you understand it. And I suggest you do that. Okay, let's try to finish up this lesson by doing the last two. And then you can go to page 3, which is, or the worksheet for lesson number 3, right? Check for the validity of this. Everyone in America watches the Super Bowl, okay? Now, you don't sit and start to analyze this. That's not true, okay? I know it's not true, but that's irrelevant to understanding or checking the validity. I want to emphasize this again. Did you get that? Don't worry whether a statement is true or not, okay? What you're focusing on is the structure of the argument. This one says, everyone in America, let's say everybody in America, here's a set of Americans, or everybody in America, watches Super Bowl. So this is saying, if you live in America, you watch the Super Bowl. Yeah, you happen to know it's not true. I know that because I live in America and I make my policy to not watch the Super Bowl. I am so defiant. Anyway, so that's not true. But the statement is saying that if you are in the smaller circle called living in America, then you watch the Super Bowl. I don't live in America. Therefore, I don't watch the Super Bowl. Where is I? in this case. I don't live in America. The only thing you can conclude is that this I is not inside of the inner circle. So I could be here, I could be here, right? It's not conclusive. And therefore, the conclusion, I don't watch the Super Bowl, is not valid. It's invalid because all you know is that this person I is not in the inner circle. It could be in the outer circle. It could be outside of the outer circle. So this is invalid. And because it's invalid, it's automatically not sound. And in fact, it's not even true because the first statement is true. This is a worst case situation. It's not valid. It's not true. And clearly, it can't be sound. All right, finally, similar, but how about these? All right, this one here. This one says, everybody in America watches the Super Bowl, okay? First statement is still the true, same thing. If you are in America, you watch the Super Bowl. See that? I live in America, so you're right here. You have to be inside of the inner circle by this second statement. I live in America, which means I am inside of the inner circle. Therefore, look, if you are inside of the inner circle, there's no way you can be outside of the outer circle, right? You, by virtue of being in the inner circle, you are in the outer circle. Therefore, I watch the Super Bowl. This happens to be a valid argument because if you're here, you cannot be outside of the outer circle. This is a valid argument. Is this sound? No, it's not sound, okay? Clear, simply because this is not true. Not everybody in America watches the Super Bowl. So you can't say, you know, just because you live in America, you must be watching the Super Bowl because the first statement is false. But if the first statement were true, then this valid structure will give you the valid conclusion, okay? So the validity depends on the truthfulness of each sentence, each premise. And if each premise is true, and if the argument is valid, we call that the sound argument. And the conclusion will absolutely be true. Okay, so that's a quick lesson in logic. All right, so this will come naturally to some of you and say, oh yeah, it's a big, you know, it's not a big deal. I knew this before. It's easy. Some of you will have a very difficult time understanding the validity and soundness and inductive and deductive reasonings. But try to, you know, understand each example, all right, to make sure that you are clear on understanding the validity of deductive argument. All right, so that will conclude this lesson. I hope you learned a lot. And now you go to complete worksheet number 3. All right, take care, and I'll see you in lesson number 4.